This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we will discuss about the Boolean Algebra, the basic theorems and properties of Boolean Algebra, and the importance of Boolean Algebra and where we are going to use this Boolean Algebra. So in this lecture, we will be discussing the Boolean Algebra, what do you mean by Boolean Algebra, and what are the basic theorems, postulates in Boolean Algebra, and also the minimization of Boolean expressions using Boolean Algebra. So here, first of all, what is Boolean Algebra? So Boolean Algebra is the basic mathematics needed for the study of the logic design of digital systems. So as we all know that algebra is a collection of principles, laws and theorems. So what is Boolean? Boolean means it is a mathematics which deals with the Boolean variables. Boolean variables are nothing but binary variables. What do you mean by binary variables? These are the variables which can accept only binary values 0 and 1. So here the Boolean algebra mainly deals with the Boolean variables which accepts only binary data 0 and 1. So we can also define the Boolean algebra as a set of elements, a set of operators and number of unproved axioms and postulates. The postulates of mathematical system form the basic assumptions from which it is possible to deduce the rules, theorems and properties of the system. So these are the mathematical assumptions. What do you mean by postulates? These are the mathematical assumptions which are used to deduce the rules, theorems and properties of a system. And these Boolean algebra was introduced by a scientist named E. Shannon, and a two-valued Boolean algebra is also called as switching algebra. Two-valued Boolean algebra means, as I told you, that Boolean algebra deals with the Boolean variables which can accept only Boolean values 0 and 1, and hence we can also call it as switching algebra. So this is the basic introduction about Boolean algebra. So Boolean algebra is an algebraic structure defined on a set of elements together with two binary operators plus and dot, provided the following Huntington postulates and postulates that are satisfied. So here that means the Boolean algebra is an algebraic structure. It is mainly defined on set of elements A and B. Together with we have two operators, binary operators. Those are plus and dot. Plus indicates the logical OR and a dot indicates the AND operation, right? So here these are plus indicates logical OR and dot indicates the logical AND. So Boolean algebra deals with a set of elements. Those elements are 0 and 1, and also two operators, that is plus and dot, provided some postulates which are defined by Huntington. So those are to be satisfied. So now let us discuss what are the basic laws and theorems of Boolean algebra, and let us try to prove them. So here, as you all know that Boolean algebra deals with Boolean variables which accepts only binary values 0 and 1. Now coming to the first postulate, that is based on the operations with 0 and 1. So we have the first postulate is x plus 0 is equals to x. X plus 0 is equals to x. Whereas, so the first postulate is dealing with binary values 0 and 1, which is x plus 0 is equals to x, whereas x plus 1 is equals to x. X plus 1 is equals to 1. And similarly, as I told you that we have two operators in Boolean algebra, that is plus and dot operator. With respect to plus, 0 plus some variable is equals to x, and 1 plus some variable is equals to that variable itself. And similarly, x dot 1 is equals to x and x dot 0 is equals to 0. So as I told you that dot operator nothing but logical and plus operator nothing but logical OR, that is logical multiplication and logical addition. So here let us consider x is a variable. So we can prove this theorems or postulates either by using the truth table or by using some mathematical derivations. So for example, the first one, x plus 0 is equals to x. Now I want to prove this one. So how can I prove this? So as I told you that this Boolean algebra deals with the Boolean variables. So x can accept either 0 or 1. So if x is equals to 0, now according to this property, theorem here, 0 plus 0, which is also equals to 0, where this is nothing but x value. We have taken x as 0 and finally the output is also, the value is also 0, and hence we can say that x plus 0 is x. Similarly, if you try this, if x is 1, so then 1 plus 0 is also equals to 1. So where x value is 1. So in both the cases, either x may be either 0 or 1, both the cases x plus 0 is giving us x. So that is why we can say that x plus 0 is equals to x. Similarly, the second one, that is x dot 1. So x dot 1 so is equals to x. Now let us try to prove this one. If x is equals to 0, so what we will get? 0 dot 1. 0 into anything is 0. Next, if x is equals to 1, so 1 into 1. So logical multiplication, 1 into 1 is equals to 1. So in both the cases, if x is 0, the value output is equals to 0. If x is 1, output is equals to 1. And hence we can say that x dot 1 is also equals to 1. And similarly, x plus 1. So here, if x is equals to 0, then what happens? 0 plus 1 is 1. And if x is equals to 1, then also 1 plus 1 is 1. Because it is logical OR operation, 1 plus 1 is also equals to 1, and hence this is proved. And now similarly, x dot 0. So x dot 0, so if x is equals to 0, then what happens? X dot 0, 0 dot 0 is 0, and similarly 1 dot 0 is also 0. That means anything multiplied by 0 will gives you 0. So that is why it is 0. So this is the first theorem with respect to 0 and 1. And now coming to the next one, idempotent law. This is idempotent law. That means when we are adding two variables to same variables, then it will give you that variable itself. That is x plus x is equals to x. In normal algebra, what is x plus x? X plus x is equals to 2x. Whereas coming to Boolean algebra, this is not valid. Where in Boolean algebra, x plus x is equals to x and x dot x is equals to x. So this is the theorem, which is this is the law, which is idempotent law. And here we have, for example, if x is equals to 0, then 0 plus 0, it is equals to 0. And similarly, if x is equals to 1, 1 plus 1 is equals to 1. So in both the cases, the output is equals to x. So that is why x plus x is equals to x. See, similarly, if x is equals to 0, then 0 dot 0 is 0. Similarly, if x is equals to 1, 1 dot 1 is equals to 1. So in this case also, if x is 0 or 1, in both the cases, the output is equals to x. So that is why x dot x is equals to x. Whereas in case of Boolean normal algebra, what is x dot x? We can write it as x square, right? But it is not valid in Boolean algebra. We have x plus x is equals to x and x dot x is equals to x. These things we have to remember. Now coming to the laws and theorems of Boolean algebra, next law, that is involution law. So the involution law states that x complement whole complement is equals to x. What is complement? Complement, this symbol is nothing but complementation operator. Complementation operator means what? Complementation means it is complementing the variable. So that means if x is equals to 0, we have only two elements, that is 0 and 1. If x is not this, then obviously it will be equals to 1. So that is here this operator complementation means it performs the not. So not of a 0 is nothing but obviously 1. So that is x complement will be equals to 1. If x is equals to 1, then x complement is equals to 0. If x complement whole complement, so that is 1 complement again becomes 0, because we have only two possibilities. If x is not equal to 1, then it will be obviously equal to 0. So that is how x complement whole complement is equals to 0. So this is nothing but again x, because we have taken x as 0, and x complement whole complement is also equal to 0, and hence I can write it as x. Similarly, this one is also same. So x complement whole complement, that is 0 complement, is equals to 1, which is again equals to x. So that is why involution law states that x complement whole complement is equals to x. This is related not only x, whatever it may be the variable, Boolean variable, how you will represent it, if x complement whole complement is equals to x only. And law of complementarity. Okay, so as I told you that this operator represents the complement operation. So x plus x complement is equals to 1. This law states that x plus x complement is equals to 1 and x dot x complement is equals to 0. So now let us try to prove this one. If x is equals to 0, then x plus x complement, x is 0 plus x complement is what? 1. 0 plus 1 is 1. Right? Next, if x is 1, then what happens? 1 plus 1 complement is 0. So again it is 1. So in either of this, that means in both the cases, whether x is 0 or 1, the value of x plus x complement is becoming equal to 1. So that is why I can generalize, in general I can write x plus x complement as 1. And similarly, x dot x complement is 0. X dot x complement. So here if x is equals to 0, then 0 into 1, x complement 0, 0 complement is 1, so it is equals to 0. Now if x is equals to 1, so x is 1 and x complement is 0. 1 into 0 is 0 again. So in both the cases the value is 0. So that is why x dot x complement is 0. Now commutative law. So this we already know this law is common in normal algebra also. So that is x plus y is equals to y plus x. In normal algebra, we used to write a plus b is equals to b plus a, right? So here also the same thing, x plus y is equals to y plus x, where a plus b can accept any value, but here x and y can accept only 0 and 1. So x plus y is equals to y plus x. So in that means whenever you are performing the OR operation, you can change the variables. You can interchange the variables. Okay. And similarly, x dot y is also equals to y dot x. That means this is the commutative law with respect to plus operator, and this is the commutative law with respect to dot operator. Okay. Now associative law. So that is x plus y plus z is equals to x plus of y plus z. So here also we can interchange the operations. So x plus of y plus z, or else we can also write this as x plus y plus z. So this is the associative law. So xy into z is equals to x into yz, or else we can also write it as xyz. So how to prove all this? So we can prove all this by using truth tables. So what is truth table and all we'll see now. So distributive laws. So where associative law deals with same kind of operator, whereas distributive law deals with multiplication as well as addition operator. That is x dot of y plus z can be written as xy plus xz. Okay, so this is the distributive law. That means I can distribute the dot operator over the plus operator. Even I can distribute plus operator over the dot operator. That is, I can write x plus yz is equals to x plus y into x plus z. So this is distributive law. And some simplification theorems we have here. So till now, these are all the laws, basic laws of Boolean Algebra. Now we are going for the theorems here. So xy plus xy complement is equals to x. And similarly, x plus xy is equals to x. So now coming to the proof of this one. So first we'll try to prove this one. So proof xy plus xy complement is equals to x, right? So here now I'm taking x as common. Then what I'll get? Y plus y complement. Already we have seen that laws of complementarity. According to laws of complementarity, x plus x complement is equals to 1. So now y plus y complement is also equals to 1. So x dot, this one is 1. So already we know that x dot 1 is equals to x itself. So this is the proof of that one. Now let us see the proof of this one. So x plus y into x plus y complement. So for proving this, so now I'm just multiplying this. So that is x into x. So here x plus y. So x plus y into x plus y complement. So here I'm just multiplying here x into x plus x into y complement plus y into x plus y into y complement. So x into x, which is equals to x itself, plus x into y complement plus y into x, I can write it as y xy, because according to the associative law, I can interchange the commutative law, I can interchange the variables, and y into y complement is 0. Okay, so now I'm taking x as common here, 1 plus y complement plus y plus 0. So this plus 0 is equal to 0. So x into, so 1 plus anything. So according to what is the law we have, this is operations with 0 and 1. 1 plus any variable is equals to 1. So now according to that, here I can, this is 1 plus something. This is equals to 1. So now x into 1 is equals to x. So the same thing. This is how we can prove this. Okay. Now this is the proof of 9th one. Now let us see the proof of the 10th one. So what is that to proof? 10th law says that x into x plus xy is equals to x. So now I'm proving this one. So here now x plus xy is equals to x. Now coming to the proof of this. So here I'm taking x as common. So in that x plus xy, so what I'm doing, I'm taking x as common. So then it becomes 1 plus y. So as we already know that according to the operations with 0 and 1, 1 plus y can be written as 1. So x dot 1 is equals to x. So this is proved. Now coming to this one. So here coming to the second law, that is x into x plus y. So how can I prove this one? So I'm just multiplying this. So I'm just multiplying this x into x plus x into y. So I can write this one as x. X into x can be written as x plus xy. So here I'm taking again x as common. So 1 plus y. So again 1 plus y can be written as 1. So x dot 1 is equals to x. So this is also proved. Okay. So this is the proof of 10th one. Now let us see the 11th one. So what is the 11th principle? So 11th theorem is x plus y complement into y is equals to xy. Now I'm taking the 11th one. So what is that? X plus y complement into y is equals to. So now I'm expanding this xy plus y complement. So y complement is what? 0. So xy plus 0. So any variable plus 0 leads to that variable itself. So that is xy. This is the 11th law. Now coming to the 11D. Okay. So xy complement plus y is equals to what? So here now we can apply the distributive law. What is the distributive law says? Distributive law says that x plus yz can be written as x plus y into x plus z. X plus z. Now based on this, where x is y here, y plus x, okay, into y plus y complement. So already we know that y plus y complement is 1. So I am rearranging the terms according to the commutative law. So x plus y into 1. So which is equals to x plus y. So this is the 11th theorem. Okay. So this is about the basic theorems, that is and their proofs here. Now let us see the another theorem, which is a very important theorem of Boolean algebra, that is Demorgan's theorem or else Demorgan's law. So here, which is x plus y plus z plus and so on whole complement is equals to x complement, y complement, z complement. This is the statement here. Now x, y, z and so on whole complement is equals to x complement plus y complement plus z complement and so on. So that means if you are writing the complement of sum of n number of variables, then that will be equal to the product of or else and of and anding the complements of n variables here. So that is the meaning here. Okay, so we cannot prove this by just simply with the mathematical expressions. We have to prove this one by using the truth table. We'll see the De Morgan's law and its proof in the next slide. Next, coming to the duality, this is one more theorem of Boolean algebra, which also plays a very important role. So x plus y plus z plus and so on to the duality will give you x into y into z. So that means what we are doing here in De Morgan's law, we are changing the plus operator to dot operator and also the variable is complemented. But here in duality, we will just simply change the plus operator to dot operator, but the variable will not be complemented. So that is the meaning of this one. Okay. So here, now similarly, x dot y dual is equals to x plus y plus z. So till now we have seen laws and theorems here. So every theorem and every law in Boolean algebra obeys the duality property. What does it mean here? So if you consider this one, xy plus xy complement is equals to x, right? So now the dual of this expression, how can I find the dual of this expression? Just changing the plus operator to dot operator and dot operator to plus operator, right? But variable will not be complemented. So here now I'm finding the dual of this one. So x plus y, because we have dot operator here. Now dot operator will be changed to plus and this is plus operator. This will be changed to dot into x plus y complement is equals to x. So this is a dual. Okay, x plus y into x plus y complement is equals to x. Similarly, the dual of this expression is this one. So x into x plus y is equals to x. This is the dual. So that means, and if you consider this one, x plus will be changed to dot, xy complement plus y is equals to x plus y, because here also on both the side we need to change the plus operator to dot operator and dot operator to plus operator. So this is a duality. So even if you observe this plus and dot here, now I'm finding the dual here. So plus will be changed to dot and the complement. Here the variable will be complemented here and this dot operator will be changed to plus operator. This is a dual. So I'm finding the dual here, x dot, y dot, z and so on whole complement is equals to, so the variable will not at all complemented here, x complement, dot operator will be changed to plus, y complement plus z and so on. So this is, that means, and similarly even if you observe here, x plus x complement is equals to 1. So now coming to the dual of this one. So the x plus will be changed to dot x complement is equals to 0. So one thing you have to remember, whenever you are finding the duality, variable will not be complemented. The plus will be changed to dot and dot will be changed to plus, and also 1 is changed to 0 and 0 is changed to 1. That thing you have to remember. Whereas in complement, plus is changed to dot, dot is changed to plus, and even the variables are complemented, and ones are changed to zeros and zeros are changed to ones. So the only difference is variable will not get complemented in duality. The remaining all the things are same here. So this is a dual of this one. And what is the dual of this one? X dot y is equals to y dot x. And similarly, if you observe this, x plus 0 is equals to x. So what is the dual here? X dot 1 is equals to x. Because I told you that binary values will also be complemented here. So that is x dot 0 will be changed to 1 is equals to x. Similarly, x plus 1 is equals to 1. So now the dual of this one will be x dot 1 will be changed to 0 is equals to 0. So this is a dual. So that means every law and theorem of Boolean algebra obeys the duality property or else duality theorem. Okay, so that is duality. And theorem of multiplying out and factorizing. So we are going to factorize a Boolean expression. So that is x plus y into x complement plus z is equals to xz plus x complement y. Okay, so this is the factorization here. Now xy x complement z is equals to x plus z dual, this the dual of this one, xy plus x complement z is equals to x plus z into x complement y. So consensus theorem, this is another theorem. So xy plus yz x complement z is equals to xy plus x complement z. So how can I write this one? How can I simply remember? So the first two terms, if you observe, xy x complement z. Okay, and then the third term is the multiplication of or else ANDing of the second variable in the first term and the second variable in the second term. So that is yz. Then I can write it as xy plus x complement z. Similarly, the dual of this one, x plus y dot y plus z dot x complement z, plus z is equals to x plus y dot x complement plus z. So here we can also prove this one. We'll see the proof of these properties. Just be patient. Now, those are all the laws and theorems which we need to remember, and these are very much useful in simplifying the Boolean expression. Why to simplify the Boolean expressions? Why we need to simplify the Boolean expression? In order to reduce the complexity of the logic circuit. So for example, if I have a Boolean expression that is a bar b plus a bar b c, we have this one. So actually, to implement this Boolean expression, how many logic gates we require? To get the complement, I need to have an inverter, and to get the product, I need to have a, so for example, I am implementing this one, a bar b, this is a, b, on the output of this one is a bar b, and similarly, we need to have a bar b, c, okay, and finally, we need to have an OR gate. So these are the number of gates we require to implement this one. So now if I apply all the Boolean algebraic principles, then I can simplify this Boolean expression. So how can I simplify this? A bar b, I am taking it as common, 1 plus c. So 1 plus c is what? 1. So that is a bar b dot 1. So a bar b dot 1 is nothing but a bar b. So then how many logic gates are required here to implement this one? 1 NOT gate and 1 AND gate. So a, b. So after simplifying this expression, I could reduce the number of logic gates required to implement this Boolean expression. So that is why we always prefer to simplify the Boolean expression by applying Boolean algebra, so that the number of logic gates required to implement a Boolean expression is reduced. Okay, so that is the use of this Boolean algebra. So by applying all these Boolean algebraic theorems and postulates, we are going to simplify the Boolean expression. Simplification means reducing the number of terms. If number of terms are not able to reduce, we are not able to reduce the number of terms, then even if you can reduce the number of variables in each term also, it is also leads to simplified Boolean expression. So that means what I want to say, simplification of a Boolean expression or else minimization of a Boolean expression is defined as reducing the number of terms in a given Boolean expression or else reducing the number of variables in each term of a Boolean expression is called as minimization. And this minimization can be done by applying all the Boolean algebraic laws and theorems on a Boolean expression, so that we will be getting the minimized expression, so that the number of logic gates required will be reduced and hence the cost is reduced. Cost of implementing a Boolean expression is reduced and even the complexity is also reduced. Okay, so that is the importance of simplification. Okay, so now coming to the proof here. So just now we have seen all the proofs mathematically. We can also prove them by with the help of truth tables. What do you mean by truth table? It is a tabular column which shows all the possible combinations of input variables and the respective outputs for all the possible input combinations. So that means it specifies the combination of all the possible combinations of input variables and also the corresponding outputs of a circuit or else of an expression for all the possible combinations of input variables. So here identity elements, commutative and commutativity complements, these are the laws here. So as we have taken two variables here, x and y. So both of these variables are binary. These can accept either 0 or 1 such that we can have four combinations, that is 0, 0, 0, 1, 1, 0, 1, 1. So x plus 0 is 0, 0, 1, 1 and x plus y and y plus x. So as we have seen that x plus and y plus x are same. So we can say that commutative law is satisfied. And x plus 0. So which is equals to x. So this column and this column are same and hence I can say that x plus 0 is equals to x. Similarly, x plus y, this column and this column are equal and hence I can say that x plus y is equals to y plus x. X complement is x is 0, complement is 1. Again 0, 1, 1, 0, 1, 0. So this is x complement. Okay, now x plus x complement will be, so I am adding these two, 0 plus 1, 1, 0 plus 1, 1, 1 plus 0, 1, 1 plus 0, 1. That means for all the combinations, the output is equals to 1 and hence I can write x plus x complement is equals to 1. Similarly, x dot 1. So AND operation with respect to AND operation. So x dot 1. So if it is 0, 0 into 1 is 0, 0 into 0 is 0, 0 into 1 is 0 again, 1 into 1, 1, 1 into 1, 1. So this column and this column are same and hence x dot 1 is equals to x here. Okay. And similarly x dot y, y dot x. So this one. And x complement, x into x complement. So 0 into 1, 0, 0 into 1, 0, 1 into 0, 0, 1 into 0, 0. So this is the proof of identity elements, commutativity and complementarity. Okay. Now coming to the associative law. So as this is the implementation of associative law using logic gates. Either we can use 2 OR gates or else we can have a simple 3 input OR gate also. A plus B plus C. So that is the output here, A plus B plus C. To prove this one, this is the truth table. So as we have 3 variables here, x, y, z. So as we have 3 binary variables, 2 par 3 combinations we'll have for the input variables. That is 8. And all the 8 combinations are this one. So that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So first we are trying to implement the left hand side equation, that is x plus y. So I'm just adding these two, 0 plus 0, 0, 0 plus 0, 0, 0 plus 1, 1, 1, 1, 1 and 1 plus 1 is also 1 because this is logical OR operation and 1 plus 1 is again 1. So this is x plus y. Now I'm adding x plus y and z. 0 plus 0, 0, 1 and 1, 1, 1, 1, 1, 1. So this is the x plus y plus z. And now I want to prove this one. x plus of y plus z. Now I am finding y plus z. This is y plus z, and x plus of y plus z. So this is x plus of y plus z. Whereas this one and this one are same, and hence we can say that x plus y plus z is equals to x plus of y plus z. So that means if we ask to prove associative law, then you have to draw this truth table and prove it. So as these two columns are equal, so I can say that this law got proved. And similarly, x dot y, this is x dot y. So dot operator is and logical and. Whenever you are multiplying anything with 0, it obviously gives you 0. So if both the inputs are 1 only, logical and operation gives 1. So this is x dot y and x dot y dot z. And now we are finding out y dot z. Okay. And then x dot of y dot z. So these two columns are again same, and hence we can say that xy into z is equals to x into yz. So this is a distributivity. So we can prove that a distributive law again by forming the truth table. So what you have to remember, first try to implement left hand side and then right hand side, and show that left hand side is equals to right hand side. And this is another way of proving distributive law, that is with the help of this truth table, and this is with the help of mathematical proof, so which we have done already. So this is the proof of distributive law. And then idempotency. So again we are proving this using truth table. Null element, that is x plus 1 is equals to 1, x dot is 0 is equals to 0. Involution, x dot x complement whole complement is equals to x. So this is the proof of these laws: idempotency, null elements, and involution. And then absorption law. Again, I hope it is clear. So as we have 3 variables here, I am taking the 8 combinations. So this is the proof of this one. The only thing is we have to prove that LHS is equals to RHS. Okay. Now coming to the another proof which we have already discussed here, xy plus xy complement is equals to x, which we have proved. This is also we proved. So these are the proofs of all the laws and theorems. Okay. Now coming to the Demorgan's law. So the Demorgan's law states that it is mainly used to find out the complement of a Boolean expression. Demorgan's theorem is used to find out the complement of a Boolean expression. How can we find out the complement of a Boolean expression? Changing the plus to dot and dot to plus operator, and by complementing the variables, and even 1 to 0s and 0s to 1s. So then we can get the complement. So this is the Demorgan's law statement, and these are the proofs. Just we are proving this by again using the truth table here. And now what is Boolean expression? Boolean expression is nothing but one or more variables can be combined in a certain way to yield a Boolean expression that serves a desired purpose. So, and one or more variables combined together to serve a desired purpose is known as Boolean expression. So, variables I am talking about. What kind of variables we need to use? We have to consider Boolean variables or else binary variables. So, this is an example of Boolean variable and Boolean expression, which includes plus operator, dot operator, and complement. As you already know that plus operator performs the OR operation, and dot operator performs the logical AND operation, and complement operation performs the NOT or else inversion operation. Okay, so now these are the basic logic gates: NAND gate and NOR gate. So this is two input NAND gate, and this is 2 input NOR gate. So here the output of this one z is equals to x dot y whole bar, x dot y whole bar, whereas this one z is equals to a plus b whole bar. Okay, so we can also represent this complement as bar also, a plus b whole bar, or else we can also write this one as x dot y whole bar. So this is we can also implement a Boolean expression using logic gates. So this is the implementation of Boolean expression using logic gates. So A into C plus D whole complement plus BE. So C plus D, first we need to implement the order of preference. So parenthesis we need to implement first C plus D, which can be implemented using OR gate, and then multiplied by A, which can be implemented using AND gate. So A into C plus D, and I want to get the complement, so I'm using AND gate, not a gate. So then I want to have BE, so I'm taking another AND gate, BE, and then I'm using an OR gate, so to which I'm giving these as input. So that is how we can implement any Boolean expression. So truth table. So as already discussed here, it specifies the values of Boolean expression for every possible combination of values of input variables. So this is the definition of truth table. Example I have given you, a bar plus b is equals to f. So I want to evaluate this value function f. So I have two variables here, a, b. So I am taking four possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. So a complement I require. So 0 is 1, 0 again, a complement becomes 1. As a is 1, a complement is 0, 0. Now I am adding these two. So this is nothing but f is a. F value is 1, 1, 0, 1. 0 plus 1, 1, 1 plus 1, 1, 0 plus 0, 0, 1 plus 0, 1. So this is f. So we can also derive the values of that like this. Now the dual of Boolean expression, already we have seen. Dual, how can we find out the dual of a Boolean expression? Simply by changing the AND operator to OR operator, OR operator to AND operator, and no variable is complemented, but the values of zeros and ones are complemented. That means zeros will be changed to ones and ones will be changed to zeros. Now we have an expression here, a complement plus b into c complement. Now I want to find out the complement of this expression by applying Demorgan's theorem. By applying Demorgan's theorem. By applying Demorgan's theorem. So as we already know that Demorgan's theorem states that x plus y is complement is equals to x complement dot y complement. Similarly, x dot y whole complement is equals to x complement plus y complement. So now by applying this, so I want to find out the complement of this one. So first of all, so I will be doing it step by step. So what is the Boolean expression we have? A complement plus b into c complement. A complement plus b into c complement. This is my f. I want to find out my f complement. So how can I find out? So f complement nothing but a complement plus b into c complement whole complement. So I have to first I have to consider this as one term and this as one term. So a complement plus b whole complement. As we have dot operator here, it will be changed to plus. And as I told you that variable will also be complemented. So a plus b, a complement plus b whole complement I have to take, and c complement whole complement. As we all know that, so again we need to apply Demorgan's theorem here. So a complement whole complement, as we have plus here, it will be changed to dot and b complement, and this is plus, c complement whole complement is c. So now a complement is a dot b complement plus c. This is my f complement. Now similarly, I want to show you the difference between duality and Demorgan's theorem. Now I want to find out the dual of f. So I want to find out dual plus b into c complement dual. I want to find out the dual. So this is one variable and this is one variable. Let us consider. So a complement plus b dual plus, because we need to change plus to dot and dot to plus, but the variable will not be complemented. So that is why I am not complementing this variable. So now again I want to find out the dual of this one. So if I find the dual, variable will not be changed, only the operator will be changed. So a complement dot b plus c complement. I hope you can identify the difference between the complement and dual. So you have to remember that the duality and complementation or different. Where in duality, variable will not be complemented, only the operators are changed from plus to 0 and 0 plus to dot and dot to plus. Okay, and even if you have any values, binary values, you have to change the binary values 0 to 1 and 1 to 0. Whereas in complement, variable will also be complemented. So we have some of the examples here. Determine the complement of this one. So I have taken this complement. So as it is, this is the first term and this is the second term. So this variable is also complemented and this variable is also complemented, whereas plus dot operator will be changed to dot. Now again I am expanding this one. So as a complement here, it will be complemented. So a complement whole complement will become a plus b complement, and this one is a complement plus b. So if I change this one, this is the, I am expanding this. So a complement plus ab, and then b complement, a complement, b complement. So this is 0 and this is 0. Finally what I'll get, a complement b complement plus ab. So this is the complement of this Boolean expression. Okay, and similarly even you can find out a complement of this one, ab complement plus c into d complement plus c whole complement. So now I want to consider this as one variable, so which is complemented here, and then plus is changed to dot and e complement. Next I have to expand this one. So now this is one term and this is one term. So ab complement plus c whole complement, this dot operator is changed to plus d into e complement. And now again I am expanding this one, ab whole complement, okay, ab complement whole complement into plus will be changed to into plus d into e complement. And then I can expand again this one, a complement plus b into c complement plus d into e complement. This is the complement. So this is the Demorgan's law and duality theorem. So this is about this is all about the Boolean algebra and various laws and theorems of Boolean algebra. And we have proved all the theorems and laws of Boolean algebra. So even we have seen the difference between Demorgan's law and duality theorem. So we will be discussing some of the simplification problems. Okay, that's all for this lecture. I hope it is clear to you all. This Boolean algebraic postulates and theorems are very important to remember. I think it is clear to you. That's all for this lecture. Thank you, everyone.
Like, share and subscribe. Hit the bell icon for more updates.